I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics, medicine, nature,
or
Space. Time.
The brain.
Life. The universe.
This week, a top to bottom tour of the intestine. Why we need more dirt in our diet, how to avoid food poisoning, and how to treat IBS, irritable bowel syndrome.
Plus, why the prospects of finding life in outer space just got a lot hotter, and evidence that touchscreen devices are affecting the sleep of children. I'm Kat Arney.
And I'm Chris Smith, and this is The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
The quest to find planets in orbit around distant stars that resemble the Earth and could be habitable has been going on for decades. But most of the early candidates are what we call hot Jupiters. These are massive gas giant planets that are orbiting very close to their parent star and they're no way capable of supporting life. But techniques and technology are improving very rapidly, and they're now sufficiently good that we can spot much tinier worlds and even, it turns out, analyse their atmospheres. And John Southworth from Keele University has done just that for a star about 40 light years away.
The star is GJ1132 and the planet is GJ1132b. And we've discovered an atmosphere around this planet, which makes it the first detection of an atmosphere around what we think is a rocky planet outside our own solar system.
Now, why is that a big milestone?
It's big because there's an awful lot of these things. The Milky Way contains about 150 billion stars. The very, very low mass stars will be the dominant component of that.
And if there are lots of them and there are planets around them, that means there are potentially lots of rocky worlds, a bit like the Earth out there.
Yes, that could be the most common thing in the universe.
You've been studying the planet which is going round this star. Tell us about that planet then.
Well, the planet's small. We think it's probably rocky. It's going round its host star every 1.6 days, so it's really close into the host star. But because the star is cold and small, then the planet itself is not particularly hot.
And how hot is not particularly hot?
It's 370 degrees Celsius on the surface.
And you can actually physically see this planet, or can you see its effect on the host star?
What we see is it passes in front of its host star once per orbit. So every 1.6 days, the star gets a little bit fainter, because the planet's blocking out some of the surface. Now, importantly, this dip in brightness actually tells you how big the planet is relative to the star, so you get a direct measurement of the size of this planet, which is not possible to do in any other way.
And can you weigh the planet by looking at how fast it's going round and how big it is? You can work out basically what it must be made of and its mass.
Yes, we can weigh the planet by measuring how the speed of the star changes, because whilst the planet is orbiting the star itself is actually going round in an orbit pulled by the planet. And so it actually changes its speed continually. And if we measure how much that speed changes, then we can measure the mass of the planet as well.
And how much does the planet weigh?
Around about 1.6 times the mass of Earth. Our results are consistent with it being rocky, but also it could be entirely water.
Oh, so you have a water world?
Yes, both these options can fit the data.
And what about the atmosphere that you're saying you can also see? How are you looking at that?
Yes, I mentioned that when the planet goes in front of the star, you get a little dip in brightness, which allows you to measure the size of the planet. Now, what we did was to measure this change in brightness at 7 different wavelengths, 4 in the optical and 3 in the near infrared. And we found that at one wavelength, which is just a little bit too red for the human eye to see, we found that the planet appears to be bigger. So our interpretation of this is that the planet has quite a large atmosphere, which is letting through light at most wavelengths. But at this near-infrared wavelength, it's actually opaque, and it's sufficiently big that it makes the planet itself look bigger. Now, if you try to make some theoretical models of the planet's atmosphere, then you can actually get this effect by using atmospheres with either steam or methane, or a combination of the two.
Right, and you can't tell at the moment which of the two it is?
No, at present our data could be entirely satisfied by either of those two things or a combination. So the obvious next step then is to get some better data and try and work out whether it's methane or water. So 3 weeks ago now I sat down to write an application to get some data from a big telescope, a very large telescope in Chile. I was half an hour into the application process, writing a science case, and I thought I'd best check that no one else had done this first. I checked the archive, and it turns out that my colleagues in Exeter have actually observed this star and this planet with a very large telescope. So hopefully, within a few months, we may actually get some more information about this planet.
God, that must be like an Egyptologist thinking they've walked in on the tomb of Tutankhamun and then discovering their mates had been there first.
Yes, but the planet was publicly announced back in 2015, so we both had the chance to have a go at it. In fact, I think we may have been observing the same transits from different telescopes in the same country without even knowing it.
And they will get, by using a much bigger telescope, better resolution of data then, will they? So
yes,
this
they'll
will
get better
enable them
wavelength resolution, which will hopefully enable them to work out whether it's methane or water, and possibly find out other interesting things about the atmosphere.
And what are the implications of what you've found?
Well, if you look at very low mass stars, they tend to form with a lot of magnetic fields, which in turn causes an awful lot of X-ray emission and ultraviolet light. Now, we think that this blows off quite a lot of the atmospheres of low mass planets near them. What we've shown here is that an Earth-like planet can survive for billions of years with this kind of radiation coming in and still retain an atmosphere. Now, we know that there's a lot of these planets in the galaxy, and therefore that means there could be an awful lot of planets with an atmosphere. Many of these will actually have the right temperature on their surface to support life. So the implication here is that life could be a lot more common than we thought.
So watch this space. John Southworth there with the discovery that he's just published in the Astrophysical Journal, and we'll be learning more about the search for life in space, but much closer to home actually, a bit later on in the programme.
Before that, though, one of the most dramatic changes over the last decade has been the explosion of touchscreen devices in our homes, from tablets and smartphones right through to laptops and electronic books. And while they are bringing us enormous convenience, not to mention entertainment, a worrying trend is emerging. These devices are also affecting our sleep, and particularly where children are concerned. A new study from Birkbeck University of London has found that up to 75% of the children they looked at used touchscreens on a daily basis, and there were knock-on effects. Katie Haler spoke to study author Tim Smith.
We asked parents to complete an online questionnaire where they documented the media environment they have in the household, how many hours a day their child used touchscreen devices, as well as some standard questionnaires on sleep, general developmental milestones like walking and language, as well as some other standard questionnaires.
And what did you find?
From those questionnaires, we were able to identify an association between the amount of time that the children spent using the touchscreens per day and their sleep behaviour. We found that the longer that the children used a touchscreen device, the less time they spent sleeping at night, and the longer it took them to fall asleep, even when we controlled for known factors that might confound the effect, like the age of the child, and even the exposure to other screens like TVs.
It feels great to get a good night's sleep, but why is it so important?
Sleep is really critical for our health and well-being. It allows us the rest to recover from the day. It allows us to actually purge our bodies of toxins and prepare for the rigours of the next day. It also is very critical for neural development and memory consolidation and learning. It allows us to actually make stronger long-term memories based on the experiences of the day. And this is even amplified when we talk about young children. Infants spend most of their day asleep, and there's a lot of development, a lot of physical and mental change happening. So anything that can actually impact sleep may have long-term consequences on their development.
And so what does this mean? Should parents be controlling the amount of time their kids spend with touchscreen devices?
Right now, we don't have any actual evidence of the consequence of this change in sleep on development, and we need to do follow-on studies to be able to identify that. But there are guidelines out there which are based on more traditional screen media like TVs that have shown negative consequences of excessive screen time, and they generally recommend to limit the amount of time that children spend on screens per day, and specifically protect parts of the day which might be critical, like the hour before bedtime, to make sure that the children don't have screen exposure and can actually prepare themselves for sleep.
So maybe tuck your kids in with a good book instead. Tim Smith there, and his paper was published in the journal Scientific Reports. You're listening to The Naked Scientist with me, Kat Arney, and with Chris Smith. Still to come, the scientist who thinks we need to live dirtier lives. But first, 2/3 of the world's population are experiencing water shortages, despite an estimated 13 trillion litres of water just hovering around us in the atmosphere. But is there a cheap and effective way to actually get hold of it? MIT's Evelyn Wang thinks so, and she's developed a device based on clever molecular sieves called metal organic frameworks, or MOFs, to do just that. Izzy Clark heard how it works.
Our device allows us to capture water from air, and the way it does it is using this special material called a metal organic framework that it acts like a sponge, absorbs a lot of this water into the pores of the material, and then releases it when we apply a small amount of heat using the sun.
How does that metal organic framework actually capture the water?
It's a device that basically is a box that opens up and so exposes this metal organic framework to the environment. The metal organic framework can capture even very small amounts of water in the air down to humidity ranges of about 20%, which are in these very arid conditions, such as desert areas where there's significant shortage of water. Then it's being able to get the water out of the material and to make it into the liquid form.
So how do you do that?
We close the door of the device, and so now the material is confined such that we can heat up the material and then releases the vapor into this local environment that is very humid because we're releasing more of the water vapor into this box. And then we can now easily condense it using a condenser from the vapor to the liquid form.
And how is that being powered? It sounds quite energy consuming.
It's a completely passive process, and because the material is tailored in a way to allow for easy release of the water at relatively low temperatures, we can use the sunlight. And then in the condensation process itself, it's also passive because we've created this local high relative humidity environment such that the condensation temperature can be near the ambient.
How much water can this metal organic framework capture and produce?
This particular MOF 801 can capture about 25% of its weight in water. Right now, we anticipate even with this amount of water capture, we can achieve a device that's about 30 liters in size or so, about the size of a carry-on suitcase, a little bit smaller than that, which can deliver about 12 to 15 liters of drinking water each day.
And so what does that mean for environments that are suffering like severe drought and water loss?
We think that this can be an important technology to be able to now address problems in those regions where there really isn't a lot of infrastructure other than, say, the sun, and often they're in very arid kind of climates. And so we hope that we can start to deploy this technology to those regions to really be able to give all these people clean drinking water. Right now, we've demonstrated a single layer of this metal organic framework in this prototype, where we want to start to now integrate a few stacks of these layers such that it can produce more significant amounts of water. And the second is working with our collaborators who have really been the experts in the chemistry and the development of the materials, is being able to now scale up these materials such that we can have larger quantities of them and to be able to then mass produce many devices.
Evelyn Wang, and she published that paper in the journal Science.
Now, we heard earlier in the programme how scientists are pointing telescopes at distant stars to spot planets with atmospheres that might be habitable. But in our own cosmic backyard is Enceladus, a small moon which, as it goes round Saturn, gets buckled by gravitational forces. And this generates heat inside the moon, maintaining a liquid ocean, and this periodically sprays jets of salty ice out into space. And by looking at what those plumes are made of, scientists have concluded that the inside of Enceladus could have all of the right ingredients for life. David Rothery is a planetary geologist at the Open University, and he took me through the findings.
Enceladus is a 502 kilometre diameter moon of Saturn, so it's an icy body, ice-covered surface. We think some rock inside, and we're pretty convinced that there's an internal ocean. The ice surface and the interior rock are disconnected by this zone of liquid water, and there must be some tidal heating going on. There are plumes being erupted through cracks in the ice near Enceladus' south pole, which were discovered when the Cassini spacecraft got to Saturn 12 years ago now, and have been studied ever since by multiple fly-throughs and so on. And the evidence has been building up and up and up about what's going on in the ocean, and in particular the interaction between the water and the warm rock at the bottom of the ocean. And that's what's got people excited, because the last bit of evidence has slotted into place that the water and the rock are reacting chemically and producing conditions down there on the ocean floor that would be habitable by the right kind of microbes.
First of all, how are these plumes being monitored?
Well, we have a spacecraft orbiting Saturn called Cassini, which will crash into Saturn this September, but it's had a dozen or so fly-throughs of the plume. It wasn't designed to fly through plumes, but once they discovered the plumes, they said, OK, we've got to fly through these and see what they are. So they retasked the mass spectrometer to analyse what's in the plume. And sure enough, pretty early on, they found there's water there. And then they found ammonia and methane and carbon dioxide. And 2 or 3 years ago, they found tiny little rock particles, little silica particles, about 20 nanometers across. And then they said, what's happening here? To get these tiny little nanoparticles of silica, there must be chemical reactions going on with the rock. If that's happening, it's a reaction called serpentinization. You make a mineral serpentine. And if that happens, you should be liberating hydrogen gas. If there's hydrogen gas being produced down there, then we've got a metabolic pathway. There are microbes on the Earth's ocean floor called archaea that can munch on rocks, provided there's hydrogen that they can use as well, and they can make their body mass out of that and extract energy from this. But the hydrogen had never been discovered. So on the final fly-through in October 2015, they retasked their mass spectrometer in a special mode, and it took them 18 months to get the results published, which have said there is hydrogen there. Everybody's convinced the hydrogen is real. That proves the metabolic pathway is viable. You could take microbes from Earth, stuff them down at the bottom of the ocean, and they'd be quite happy there.
Is there any other rational explanation for why this hydrogen could be there?
Well, you can get hydrogen by a little bit of radioactivity can break water apart, but it seems that it can't produce hydrogen at the necessary rate.
Does this mean then that, given it is the end of Cassini this year, and our opportunity to study this further is now effectively at an end, that we need to push up the agenda for the European Space Agency, also other space agencies around the world, new missions like Cassini, and focus on Enceladus? Is that where the money should go?
Well, you're right. There's no more information to come about Enceladus from Cassini. Enceladus isn't the only place to study. There's Europa, a big icy moon of Jupiter, bigger than Enceladus, and plumes haven't been seen by a spacecraft around Europa, but you can see them by the Hubble Space Telescope. So there are spacecraft heading to Jupiter. There's a European Space Agency mission called JUICE. There's the Europa Clipper, funded by NASA, going to Jupiter to study Europa and the other moons. But Enceladus also should have a mission. There's one called the Enceladus Life Finder, or ELF, which is a lovely name, which was proposed in a recent round to NASA, not funded. NASA's funding 2 asteroid missions this round, but I suspect that ELF will come back next year and perhaps will get funded, because Enceladus really is a high priority target. So Enceladus and Europa, either of those are places to go, and if we can nail down the fact that life does exist there, that ought to change our outlook on life in the universe, because if it's in these other places, it will be all over the place around other stars too.
And presumably it must focus minds in terms of being extraordinarily careful about contamination.
Yes, we certainly don't want to accidentally seed anywhere with Earth life. And this is why at the end of the life of Cassini, it is being crashed into Saturn. It will burn up in Saturn's atmosphere. And no bugs which have accidentally hitched a ride from Earth and have survived 20 years in space will get down to anywhere habitable. Space agencies are careful. They have to be by international treaty not to accidentally take Earth microbes anywhere where they could survive.
It's certainly an amazing time, isn't it? David Rothery there, commenting on the work which came out in the journal Science. Saturday, the 22nd of April, was Earth Day, and it saw thousands of people across the Earth join the March for Science. There were 5 of these across the UK, the biggest one taking place in London, and there crowds gathered outside the Science Museum and then marched towards Westminster's Parliament Square. And our own Izzy Clark was there to see what was going on.
Science, not silence! Science, not silence! Science, not silence!
On Saturday, the 22nd of April, thousands of scientists and science supporters took to the streets in over 500 locations across the world to join the March for Science. Created as a celebration of progress and a call for governments to encourage research, 5 marches took place in the UK in Bristol, Edinburgh, Norfolk, Manchester and London. I'm Izzy Clark, and I spoke to comedian and science broadcaster Robin Ince, one of the speakers at the London March, about why this international movement was taking place.
It's the idea of having to stress the importance of science communication, the importance of politicians understanding contemporary science, and the fact that they need to keep open dialogues with scientists. But also there are some fears with the Scientists for EU movement that when we leave the European Union we will possibly be burning some of our bridges with some of the scientific community in Europe, and the importance of reminding people we must not do that. Science is something that is an international movement. It does not have to be fenced in by national boundaries. In fact, it's very important that it's not fenced in by national boundaries. That is one of the beautiful things about CERN. CERN was about bringing together scientists from across the world and working in unison on something positive.
And this is taking place all over the world. It's very much an international march. Why now?
My sense is that over the last couple of years there has been in the mainstream an appearance that perhaps ideas of tolerance, ideas of curiosity and ideas of moving forward with knowledge perhaps need greater defending than we'd imagined. There seemed to be a sense that there's a retrograde step going on in terms of us as human beings, and I think it's to remind people that we need to keep moving forward and we cannot be complacent. And I think we're beginning to see amongst people, including us, so everyone here, it's very easy to become complacent because we've had comfortable lives, much of that powered by science and technology.
One campaign group that aims to provide a voice for scientists is the organisation Science is Vital. Their chair, computational biologist Dr. Andrew Steele, explained what they do and why scientists are concerned about funding.
Science is Vital kicked off back in 2010 with a protest outside the Treasury protesting the government's threatened spending cuts for science funding. And since then we've sort of carried on reacting to various different bits of news and protesting mainly about science funding but also about other wider issues in science and trying to provide a grassroots voice for scientists and supporters of science.
With funding being cut, is that quite a common occurrence at the moment?
So science funding's in a very funny place right now. The government are very keen to make the right noises about science. But if you look at what's actually happened to science funding in the last 5 or 10 years, then basically, since the last government took power, it's been a bit of a downward direction. Now, in the autumn statement, the Chancellor George Osborne did announce this extra £2 billion for science. But there's still a lot of uncertainty about, firstly, how that money is going to get spent, and secondly, whether the whole thing is just going to be cancelled out by Brexit.
And the lack of funding, is that just related to researchers or does that extend to the public?
European funding extends to all kinds of different areas. Things like agricultural subsidies and some regional development money for places like Cornwall and Wales are funded from the EU. But it makes a huge, huge difference to scientific research. About 10% of the UK's total public spending on R&D comes from the EU. And that can definitely affect everybody's lives. Research looks at things like answers to questions in health, answers to how we can generate our energy sustainably into the future. So even if it were only to hit research, that would definitely have huge impacts across the UK.
And why do you think marches like today are important?
I think the most important thing about today's March for Science is it provides a focal point. We marched back in 2010 and scientists haven't marched in the intervening 7 years. And I think the problem is we just don't like getting angry. But there's room for some evidence-based anger here. We've got attacks on science from members of the government in countries all across the world. We've got funding being threatened or funding being cut in different places. And I think this just provides the opportunity, a flashpoint for scientists and science lovers to come together and be a political voice.
I'm marching because climate change is real and we did cause it.
I'm marching because science isn't being taken with the kind of respect that it should be.
Because evidence-based veterinary medicine is very important.
I'm marching because science is the best way we have of understanding the universe, and I think that we should understand the universe.
I'm marching because alternate facts aren't peer-reviewed.
I'm marching for evidence-based policy making.
Whatever the reason, thousands of people turned up across the world to show their support for science. At the end of the day in London, I caught up with guest speaker Dr. Suze Kundu to talk about how the march affects the general public.
The majority of this crowd that we're here today were made up of scientists, or what I like to call the sci-curious people that are already engaged with science. Really what we need to be doing is breaking out of our little bubble and actually engaging with the rest of the public. And hopefully, if people have seen the friendly side of science, and the approachable side of science, and the normal side of science, because ultimately we're just people too, hopefully they'll feel more empowered to want to engage with us. So I think this is the first of many things, but we need to maintain that, and I think everybody just needs to act on the positivity of today.
And what would you like to see achieved from today?
One of the things I mentioned in my speech earlier was the fact that we need, each and every one of us that's here today, ideally would speak to somebody that wasn't here today, to speak to them and tell them about why they came here and what they found out from people and what we can do. Because ultimately, over there in Parliament, the people that are making decisions are making them on behalf of everyone. And so people that are funding our research need to take a bit of ownership of that and feel proud in taking some ownership of the science that goes on in this country and abroad as well, because it's for them, it's paid for by them, we want them involved, and we really feel they should be involved.
Hear, hear. Suze Kundu there, and before her, Robin Ince and Andrew Steele, and they were speaking with Izzy Clark. You're listening to The Naked Scientist with me, Chris Smith, and Kat Arney. In this half an hour, we're going to be navigating the twists and turns of our digestive systems, and we're taking a top-to-bottom look at what's going on inside your intestines. On the way, why a bit of dirt is good for you, what happens when food poisoning comes to town, and what's irritable bowel syndrome, and what can we do about it.
But first, you might not think of your mouth as being part of your gut, but the long, hollow tube that is the digestive system starts right here. Food, drink, and rumour has it the occasional spider, and maybe my fingernails, go in and digestion begins, powered by your saliva and your teeth that turn big chunks of food into bite-sized morsels that are easier to swallow. But as many people have been made all too painfully aware, our teeth can decay. And according to the most recent Children's Dental Health Survey, about 50% of 15-year-olds have evidence of tooth decay. But why? And what can we do about it? Chris Vernatzer is a paediatric dentist at Newcastle University, and he's the co-author of that study and joins us now. Hi, Chris.
Hello.
What is causing this tooth decay? What actually makes our teeth kind of rot and have problems? What are we talking about?
Yeah, okay, so we need a few different ingredients for tooth decay to actually happen, and maybe the principal one of those is actually the bacteria that live in your mouth. And the mouth's home to billions of bacteria, and all sorts of different species as well. We think there are about kind of 500 to 700 different species, but it's when these all get out of balance with each other that actually the decay starts.
What is the decay? How do bacteria make our teeth break down? What goes on there?
Yeah, so the bacteria, if you like, feed on sugar, which is what commonly people will recognise as a major ingredient of decay. And as they feed on that sugar, they metabolise it and produce acid as a waste product and excrete that out of their cells. And it's the actual acid that's attacking the hard bits of the teeth, the enamel, that leads to them dissolving away and then creating holes in the teeth.
So it's the acid created by the bugs that breaks down the structure of our teeth. And you've said that it's the sugar that the bugs are feeding on that's doing this. So is that presumably just things like sweets? Where does this sugar come from?
Yeah, so we're really interested in what we call free sugars, and that would classically be things like sweets, cakes, puddings. They're the very obvious ones that people think about. And increasingly, people are also thinking about drinks as well. So sugary drinks have been much featured in the news of late as a major problem for obesity, but also a major problem for tooth decay. But there are other forms of free sugars that are more hidden away. And so that might be things like honey, which people might think of as quite healthy, but actually is very bad for teeth. Dried fruits, because they've dried the sugar that's naturally bound up in the cells and isn't really available for bacteria to make decay from, actually begins to get released. So dried fruits particularly bad. And fruit juices as well can be quite problematic because, again, the fruit's been blitzed and the sugar's been released from the cells.
These are all things that are meant to be super healthy for us.
Yeah, absolutely. And that's a bit of a problem for us because often people will turn to those as a healthy alternative, but actually they're actually damaging their teeth quite badly.
So what should we do? Because I'd be the first to admit that I do love sweeties, but I also, I like fruit and I like fruit juices and dried fruits and honey and things like that. What should I do? Should I just stop eating them? That would make my life miserable. How do I protect my teeth?
Yeah, so in an ideal world, we would like everyone to stop eating them, but of course, that's probably not a reasonable way of doing things. So as well as the amount of sugar that you eat, the really important thing for teeth is how often you eat them. And every time you eat some sugar, the bacteria produce this acid for about half an hour afterwards. The saliva actually brings the acidic environment back to a normal environment. So it takes about half an hour for that to happen. So you can imagine if you're having a sugary intake every half hour, your teeth are constantly under attack. Whereas if you reduce the number of intakes, then there's going to be a safe period between each where your teeth can kind of begin to remineralize and grow back again, if you like.
So that would argue for just eating your sweets or sweet stuff at once or at only a few points during the day rather than constantly dipping into your pockets and snacking.
Absolutely. So one of the common things we advise our patients is if they can have sweet things with their meals, then we know that the teeth are only going to be attacked at meal times and sticking to non-sugary things between meals.
And what about things like toothbrushing? Because, we're all brought up to brush our teeth in the morning and at night and do things like flossing and all that sort of thing. What should we be doing there?
Yeah, so as I've said, the decay happens when the kind of bacteria get out of balance. There are lots of naturally living bacteria in the mouth, and the bacteria grow in these communities that we call plaque. That's the furry stuff that sticks to your teeth. And as the plaque gets more and more mature, the bacteria begin to select out themselves as the ones that are going to cause more decay. So if we can disrupt that plaque by removing it, then that will be very beneficial in preventing decay, which is why brushing is so important and flossing to get between the teeth. So our recommendations are to brush twice a day with a fluoride-containing toothpaste, and the fluoride's really good at preventing decay, both because it stops the bacteria producing as much acid, but also it means the teeth become harder and less susceptible to the acid. So brushing twice a day with a fluoride toothpaste is the key there.
And very briefly, we've mentioned this report that shows that almost 50% of 15-year-olds have tooth decay, which obviously is not great, and later in life they could be losing their teeth. But is there a trend here? Are the nation's teeth getting better, or are we just descending into horrible teeth forever?
No, so things have actually got quite considerably better over the last 40 years, and a lot of that has been driven by the addition of fluoride toothpaste. So if we look at the 15-year-olds, when we first did the survey in 1973, 97% of 15-year-olds had some kind of cavities, wow, which was a shocking figure, and that's gone down to 42% in 2013. So we have seen big improvements, but I think the fact that we're still sitting just below half of 15-year-olds with some kind of cavities or having had experience of them is really quite shocking when it's a completely preventable disease.
Thank you very much. That's Chris Vanatta from Newcastle University, and hopefully explaining that we have gone some of the way to beat the US stereotype of British people having terrible teeth.
Now, downstream of the mouth is your esophagus and then the stomach, where food gets further digested by acid and enzymes. It's then released slowly into the small and then the large intestines, which together make up a 7-metre long tube where nutrients and then water get absorbed into the bloodstream. But that's not all the intestines do, because in recent years we've realised that they also provide a home for an additionally previously unrecognised organ, which weighs more than your brain, and it also plays a huge role in keeping you healthy. Guessed what it is yet? Well, that organ is your microbiome, the collection of microorganisms that live inside you. And studying the microorganisms and the microbiome is the preserve of King's College London scientist Tim Spector.
It's a community of microbes that inhabit our bodies, and 99% of them are actually in our lower intestine, the colon. There are 100 trillion of them. Most of them are bacteria. As well as those, there's 5 times as many viruses. There are also fungi and other little parasites as well. And together, these 100 trillion microbes weigh several kilograms. And one way of looking at them is not as a disparate group of bugs, but actually as a newly discovered organ in our bodies, because they weigh pretty much the same as a large spleen or your brain. And we're just discovering how many different things they can do and how they help us survive.
How did they get there in the first place, Tim?
The way they inhabit us starts at birth, because we are pretty much born sterile, and we get our first microbes through the birth canal. These microbes get down into the infant's guts and start proliferating, which allows you to then go on and develop normally and have a normal immune system and a defense system.
And this is a community of lots of different types of bacteria, which we pick up from the environment, some of which suit us, some of which don't, some of which therefore thrive, some of which don't. And so we end up a bit like a meadow with lots of different flowers and grasses growing in it. That's our microbiome.
Yes, I think the garden analogy is exactly that, and not forgetting just the meadow on top, it's also the soil underneath, the mixture of fungi and microbes. A good, healthy microbiome community is one that is extremely diverse, has lots of different species all working together so that no one group takes over. Every little grain of nutrient is used, and every byproduct of every microbe goes to another microbe, and so nothing's left to waste. These guys are constantly producing things for the human body we didn't think were possible, because as well as having about the same number of cells as the average human, they have 200 or 300 times more genes than we do, that not only help us digest complex carbohydrates, which we couldn't otherwise eat or get nourishment from, they also are key messengers for our immune systems. They also produce a third of our vitamins and brain chemicals, so they can influence our mood and even our appetite.
Now, you said that they get there by the birth process, but not everyone's born the same way and not everyone's breastfed. So what are the influences of not having a normal vaginal delivery or not being breastfed? Does that change the spectrum of bugs?
We're only just finding out the real issues here of this epidemic of caesarean sections, which currently is about 23% of the UK, but many parts of the world it's over 50%. There were thought to be no downsides, but we do know that the microbes of the first 3 years of a baby's born by caesarean section is very different to that provided by the normal birthing process. It turns out that this isn't particularly healthy for them, and there's a slightly increased rate of obesity and allergies in children born to caesarean section, something we didn't really think about at all before. We just thought it was a routine operation that would have no consequences.
Now, that's babies having the wrong bugs from birth, but what about adults? Are there any examples of adults where the spectrum of bugs in the gut goes off kilter and that's linked to adult diseases?
If you take a group of people with a disease or a disorder and compare them with healthy controls, there's one consistent finding in all of these studies is that the diseased people have less diversity of microbes.
Is that because they're taking drugs for their disease, or they've got their disease and that's influencing the environment these bugs are being asked to thrive in? Or did the bugs change and that caused the disease?
Well, you can't tell just from the human studies, because it could be one or other, or it could be both. We did this in a study where we found some microbes associated with being thin, and we took those microbes from our twins and we put them into germ-free mice. And we found that with those skinny microbes, you could overfeed these mice and keep them still skinny. And so it turns out that if you look at the majority of diseases, some are undoubtedly caused by having the disease, but it's also the case that those same individuals lack protective microbes, that when you give those protective microbes to other animals, you can prevent them getting the disease. So it's probably a complex mixture of being unhealthy makes you have an environment which stimulates more bad microbes to be there, but it's also initially the lack of good microbes which seems to be predominant. And I think that's really telling here, because we've been in the past focusing on microbes as the enemy, use of Domestos and other sprays saying you must get rid of microbes and you mustn't get infected. It turns out possibly the reverse is true. The more microbes we have, the more we might be protected against all kinds of diseases.
I suspect you get asked this a lot, especially at dinner parties, where people will turn to you and go, so should kids be eating more dirt? Would you say yes then?
if I had to give a short answer, the answer it would be yes. There is pretty good evidence that playing in a healthy garden, getting dirt on you, playing with animals, being exposed to many of the rural microbes that we've lost is generally good for you. Next week I'm going to Tanzania to the Hasda hunter-gatherers, and these people live like we used to live. They eat everything that's around them, and the concept of dirt doesn't really appear. And they have 40% more species than healthy people in the West, many of which, we've just eliminated through our obsession with hygiene, overuse of antibiotics, and, our move to cities, which only attract certain types of microbes. So I think it is crucial that we relook at this whole idea, particularly in the early life in kids, by moving back from this over-sterile world and realize that in these, what we call more primitive environments, they really don't have allergies or autoimmune diseases, which are reaching epidemic levels just in the last 30 years in most Western countries.
So a bit of dirt might do you some good. Tim Spector there from King's College in London. This is The Naked Scientist with me, Chris Smith, and also with Kat Arney.
So far, we've travelled from the teeth to the large intestine and met the microbiome, those microbes that help to keep us healthy. But I want to take a short detour back to the stomach for a moment. This is the biological vat of acid that's a very effective defence mechanism against bacteria, but the bad kind. But some germs do get through and, once in our intestines, can cause the kind of infection that most people call food poisoning, and millions of us succumb every year. University of Liverpool infection biologist Paul Wigley is with us to explain where these infections come from. Hi, Paul.
Hello there.
So when we talk about food poisoning, we might think of you go for a meal and then a bit later you find yourself throwing up, you've got diarrhea, it's all going horrible. What has actually happened there? What is food poisoning?
Well, it can be one of two things. In the real strictest sense, food poisoning is getting a toxin within food, usually due to poor storage or poor handling. And this is typically very quick onset diarrhea or vomiting, but fairly short-lived. And with the exception of botulism, which is very serious, these don't tend to be particularly serious conditions. But the second and more serious is where you actually have an infection, usually by a bacteria like Salmonella or Campylobacter, that can survive very well passage through the stomach, colonise the gut, and there cause damage within the gut, leading to more prolonged and often more serious gastroenteritis, diarrhea, vomiting, and in some cases this can be life-threatening.
So you've got the sort of the in and out kind of food poisoning that's caused by toxins. So that's things that have been produced by bacteria, but it's not the bacteria themselves.
Not the bacteria themselves. That's the one I would call the dodgy takeaway diarrhea rather than something rather nasty from meat, eggs. Or,
okay, so having like
instance.
A rough night and you're better in the morning. But then in terms of the bacteria that do get in and set up an infection, how does that happen? Because the stomach is really acidic. How do they manage to survive and then get into our body and cause us harm?
Well, they've got a lot of challenges. The stomach is one of the first ones they have to deal with, and the stomach is very acidic. And if you think, we have a long tradition of using vinegar, which is about the same acidity as the stomach, to preserve food because it kills bacteria. Now, enteric bacteria, those able to infect the gut, have developed mechanisms where they can adapt to acid conditions. And they do two things. First, they can change the surface of the bacterial cell to make them far less susceptible to the hydrogen ions that cause the acidity. And secondly, they can pump out the hydrogen ions from inside the bacterial cell, thereby allowing them to maintain a more neutral pH within the bacteria.
So once they've got through our defences like that, they go down into the intestine. And just sort of quickly, how do they actually make us ill? How do bacteria in our intestine make us sick if our intestine's so full of bacteria anyway?
Well, obviously, the intestine's full of bacteria, so they have to be able to compete against the microbiota that's already there. And usually they have to attach to the side of the intestine. So usually they have projections like flagella or fimbria, which allow them to stick to the enterocyte, the cells of the gut. There they can do two things. They can produce a toxin, so things like traveller's diarrhea caused by a type of Escherichia coli, E. coli, is an enterotoxin, but things like Salmonella and Campylobacter tend to cause damage to the cells. They actually inject proteins into the host cell, changes their structure and function, leads to inflammation. This causes damage to the gut, very painful, very uncomfortable, and also can lead to diarrhea, fever and vomiting.
Oh, you give me flashbacks. I had a horrendous gut infection a year ago. But say we're getting towards barbecue season, which is a common way that people do end up accidentally picking up food poisoning. What should people do to minimise their chances of getting either the toxin-based food poisoning or picking up nasty germs?
Well, it's very important to handle food very well within the kitchen. Or indeed, if you're cooking a barbecue, if you handle food, you have your fingers all over it, you've got those bacteria on your skin, some of which can produce toxins that can cause diarrhea.
And presumably people not washing their hands after they've been to the toilet and things like that.
Absolutely, yes. I have two children, and it was a constant battle when they were younger to get them to do that. But I guess the biggest problem when we think of a barbecue with bacteria like Campylobacter, which are very prevalent in chicken within the UK, there you really need to make sure that you handle meat with respect. You've got to consider that there's a high chance of a piece of chicken has Campylobacter upon it. Avoid cross-contamination in the kitchen. And if you're cooking chicken on the barbecue, make sure it's cooked through. Make sure it's not pink in the middle. And the other thing is, don't wash chicken before cooking it, because all you're going to do is create an aerosol of Campylobacter in your kitchen. And 2-3 days later, you could be well regretting that.
Ew, so that's a very timely tip for us all. Thank you. Just remember to keep things clean, cook your chicken thoroughly, and don't wash it. So that's Paul Wigley from the University of Liverpool. And we can all agree that food poisoning germs are definitely foes rather than friendly bacteria.
Now, another problem which afflicts the intestine is irritable bowel syndrome. And actually, up to 20% of adults in developed countries are affected by this phenomenon, IBS. But what actually is it, and how can it be treated, if indeed it can? Well, April is actually IBS Awareness Month, so we thought we'd better find out. And Anthony Hobson's with us. He's from the Functional Gut Clinic in London, where he's a clinical scientist. Hello, Anthony. So what actually is IBS?
Good evening. So IBS is characterised by a set of symptoms. So symptoms like bloating, abdominal pain, altered bowel habit, and really it's a diagnosis of exclusion. So what I mean by that is if you go to your GP, with those symptoms, then what he will do is to try and exclude a serious cause for those things. So things, red flag symptoms such as bleeding, weight loss, and so forth. And if he's quite confident that these symptoms are not caused by anything more serious, then he will give you a diagnosis of IBS. If you find yourself in secondary care, then that diagnosis of exclusion goes further with things like stool tests, imaging tests and colonoscopy.
Well, tell us a bit about those. So someone comes to you with a set of those symptoms. What sorts of things will you do to them in order to work out what is causing them to have IBS-type symptoms?
There's a kind of triage process which a lot of patients should be able to treat their symptoms with self-help. So there are lots of good self-help guides out there from places like the IBS Network, which can help you to modify your diet, for instance, and try and eliminate those things that cause most of your symptoms. However, some people can't do that. So the next process is to, with the NICE guidelines, is to seek care from a dietitian and who can help you to modify your diet and treat things in that way.
So is it usually a change of diet that triggers it then? Or is it just that it comes on in some people at some point and then they've got to deal with it?
It can be like that in terms of people will change their diet. They may go to a different country, or they may start eating a different diet, a healthier diet maybe, with a lot more fruit and vegetables, and that upsets the system. But there are other causes for IBS as well.
And say this happens to somebody, I mean, what sorts of tests, because I know you said you can get investigated, but what sorts of things are you measuring from somebody which would then say, yes, we think this is IBS and therefore the right sorts of treatments will be X for you?
Okay, so even before you get to diagnostic tests, then the things that you can do is to try and exclude something. The commonest one is the protein gluten. So people will do a gluten exclusion test, see if they feel better, and then reintroduce it and see if symptoms come back. A similar thing can be done for milk proteins. So things like beta-casein, there are different types of milk proteins. So the A1 protein in regular cow's milk can have more of an immunological effect as compared to A2 milk, which is from older breeds of cattle, goats and sheep. So it's a simple test that you can do yourself to try and understand whether your body is digesting things properly.
I did hear one person say that actually what probably is happening is that some component of the diet in some way selects for a certain cross-section or population of microbes, and this shifts the whole population, a bit like a bacterial domino effect going off, and you upset the apple cart. And that then causes the symptoms. And actually, by withdrawing certain foodstuff slowly, you encourage the microbiome to reset itself.
Certainly, as the other speakers alluded to, complex carbohydrates get broken down in the colon. And if you have too many of these, or you're not absorbing these carbohydrates properly, such as fruit sugars or milk sugars, then this can affect the microbiome. And by withdrawing those difficult to digest carbohydrates, then you can reset the microbiome and get rid of some of those symptoms.
One thing that we covered a few weeks ago on the programme was an apparent link between stress and IBS, and people were saying if they make an animal or take a human who's stressed, who's got IBS symptoms, they can take some of the bacteria from their gut, give them to animals, and they can make an animal have IBS, like it's almost transmissible.
The microbiome can release certain neurotransmitters into the lumen, and that can affect your mood. The way we look at it is there's two types of stress. There's a physiological stress and there's a psychological stress, and both have a bidirectional influence on IBS symptoms. So if there's a period of inflammation like food poisoning, then this can create a physiological stressor, and that can change the local environment, and vice versa. If someone is stressed or bereaved, then that can also change motility and make the gut more suitable for different types of microbes.
When you take someone on and help them, what proportion of people do you think, with the sorts of interventions you've outlined, you can get better?
Again, it's a triage process, so I think many people can deal with these symptoms themselves. If they can't, then they need testing. One of the things we can test for is if the bacteria has stayed in the small bowel and has started to affect the way people digest food. This is called small intestinal bacterial overgrowth. It can be tested for with a hydrogen breath test and treated with a specific antibiotic, but that tends to be done only when you've gone through these first stages.
So you start simple and sort of escalate.
Yeah.
Anthony, thank you. That's Anthony Hobson from the Functional Gut Clinic. And thank you to our other guests this week as well, Paul Wigley, Tim Spector and Chris Vernatza.
And now it's time for our question of the week. Izzy Clark has been investigating this colourful conundrum from David.
While walking my dog in the evenings during the holiday season this year, I noticed I was unable to focus on and clearly resolve the dark blue LEDs in Christmas tree lights or fairy lights. For all the other colors, I could resolve the shape and even the texture of the individual light bulbs. But with these deep royal blue LEDs, all I could see was a hazy blur. Why is that?
Here's Dr. George Dobre from the University of Kent to shine some light on this colourful query.
The cells in our eyes that process colour are called cones. It's easy to remember, cones for colour. And they can be found at the back of our eye, called the retina. These cones really detect just three colours, red, green and blue. We then build other colours based roughly on the amount of red, green and blue the cones report to the brain. However, the blue cones are a small minority, only about 10% of the total.
So each cone is set to tell the brain about mainly one of these three colours. But as more cones register red and green light, blue is at a slight disadvantage. But why does blue light appear blurry?
To be able to see a tiny dot of colour, like a blue LED, in detail, the eye needs to be able to focus that LED light on just a small number of cones. The smaller this area can be, the more detail we can see, but for a blue dot that's difficult to achieve. The eye automatically adapts to see red and green with the sharpest focus, which leaves the blue unfocused and fuzzy. This is called chromatic aberration.
The human eye has evolved towards a compromise. We still see sharp images most of the time, except for when we look at tiny blue dots or lines. And that's because it's a relatively rare occurrence in nature. That's the anatomy and physiology part covered. Come on, George, hit me with some physics.
The physics part of the answer has a lot in common with the question, why is the sky blue? Which also applies to these blue fairy lights. Being at the short wavelength end of the visible spectrum, when blue light hits air molecules, it scatters much more than red or green. In contrast, red light at the long wavelength end of the spectrum tends to scatter less, continuing along in mostly a straight line, which is why we get red sunsets. The consequence is that blue light is focused to a spot on the retina that's a little bit bigger than that for red and green.
There we have it. It's a combination of our eyes adapting better to red and green light, plus the fact that blue light scatters across a larger area on our retina. Next time, we'll be tuning into John's musical matter.
As all sound is simply vibrations in the air, and therefore musical notes are the same, then why do we hear the same note as a different sound when played on different instruments? Why does an A sharp played on a piano sound different from an A sharp played on a trumpet?
Fantastic question. If you think you can answer it, email chris@thenakedscientist.com. You can find us on Facebook, tweet @NakedScientists, or join the debate on our forum, nakedscientist.com/forum.
And that is it for this week. Thank you very much to Katie Haylor for putting the programme together. And do join us next week when we're zooming in on cancer. The Naked Scientist comes to you from Cambridge University and is supported by the STFC, the EPSRC and Rolls-Royce. I'm Chris Smith, and thank you very much for listening. Goodbye.